All right. Good evening, everyone. Welcome to the 10th problem solving session of the course Aeroengine gas turbine cycles. In the week 10, content includes turboprop engine. So we successfully completed turbofan engines till week 9. And now it's a turboprop engine for the week 10. And for week 11, it is going to be turbo shaft engine. Okay. So what we will do today is we will quickly go through what the the contents of week 10 and quickly give a recap, and then we will solve one problem in turboprop engine as usual. And yeah, so that is the agenda that I have today. So currently there are no participants. I think most of you are comfortable viewing this in YouTube, but if you have any doubts uh, regarding the problems, please let me know. And yeah, come back to the next session. And if you have any doubts, you can ask me, or you can also you can also ask in the common forum. Okay. All right. With that information, let me check my recordings. Yes. Okay. So in week 10, as I said, we studied about turboprop engine. So turboprop engine is um, you have a propeller as your main propulsion component. Basically, the nozzle thrust is minimal. So nozzle thrust we do not focus that much, but with from the propeller, the amount of air the propeller displaces will give a uh, push towards the forward movement of the aircraft, so that due to reaction, and that thrust is what we are interested in. And uh, if we rotate the propeller or if we give high power to the propeller, you are going to get higher thrust. And so that is the idea of the turboprop engine, but the energy is coming from the turbine. Okay, so typically you have like a single spool turboprop engine or a dual spool turboprop engine. In a single spool, as the name says, you are going to have turbine, compressor, and the propeller in the same spool. In fact, there will be a gearbox between the compressor and the propeller. So whatever the energy extracted at the turbine is first some part of the energy or work is provided to the compressor here, and the remaining part is used to drive the propeller. And this propeller is going to rotate. The propeller diameter is very large, and you do not have a duct. If you have a duct over here, it becomes a turbo fan engine in a way, right? So um, we do not have a duct. This propeller is a free turbine, okay, like a free uh, device that is going to keep rotating, and it is much larger than the typical turbofan uh, fans. So here you have this propeller, and in a dual two spool turboprop engine, you have the HPT turbine which runs the compressor, and there is another separately power turbine or the low pressure turbine. The power turbine is directly going to rotate the propeller. Okay, and as I said, the thrust you will get through the propeller is very large, and the thrust the main goal here is to extract as much as energy from the in the power turbine stage and provide it to the propeller. Okay, and the remaining goes out of the nozzle, that is going to provide some amount of thrust. All right, so this is typically used at low speeds, and what advantages it provides is like it has high thrust to take off, uh, uh, and you have high fuel efficiency, even more than turbofan engines you can get. um, the frontal area is less, wide range of speeds, easy to maintain and low vibration, multi-shaft arrangements. You can have adapted to variety of sizes and also configurations, and especially VTOL, vertical takeoff and landing applications. You can use this turboprop engine. So basically, you can tilt the entire engine in a way that you can change the direction of the thrust, and that will be used for takeoff and landing. Um, so people typically use this for smaller aircrafts like the what do you call the goods freight aircrafts, basically. um, so that you transport the goods with a very low um, fuel, right? So very uh, in the most efficient way, at a minimal cost. So that's why people typically use this. They also use it for UAVs, like drones, for military reconnaissance and surveillance. All those things people use. So for wherever cost effectiveness is required, people use this turboprop engines. So the challenge is, at higher speeds, your propulsive efficiency decreases. Um, but at a lower speed, it has a good propulsive efficiency, limited to, of course, subsonic flight. You cannot go supersonic here. Additional weight, pitch control, reduction gear, power turbine. So all these things adds as an additional weight. The cost goes up, and you have like gearbox, which has like many moving parts in general for this. So turboprop engine, the calculations kind of remains it remains same till the combustion chamber. In the turbine, you have to slightly change a bit, because now um, the work is done to drive both compressor and turbine. For example, in this single spool turboprop engine, the work extracted at the turbine has to drive both compressor and propeller. Now, what is the amount of power that is available to the propeller? How do you calculate? First, between the compressor and turbine, you have a power transmission, which is work done by turbine times the efficiency of that uh, uh, efficiency of the turbine. Sorry, efficiency of the transmission. And then between compressor and the gearbox. So in between the compressor and gearbox, you have the MC efficiency, and then between gearbox and propeller you will have like gearbox efficiency, which you need to multiply, and then finally all the power provided to the propeller is not exactly used, so you have again a propeller efficiency. So this is the total power available at the propeller. Okay. And um, the total amount of energy that is available at the end of combustion chamber or at the inlet of the turbine is going to be 4 to complete expansion, right? To 9s, or yeah, to 95. I guess it should be 9s anyway. In that, there is a power split. So how much has to be going to compressor and how much has to go to uh, propeller. So that power split is given by alpha, and we will solve one problem, you will understand it better. And so in the turbine stage, you have like alpha times the total delta H ideal, and 1 minus alpha times the total delta H is at the nozzle stage. Okay. um, and in the nozzle, you typically these nozzles are unchoked, so that's why we directly took the unchoked velocity expression. And the propeller efficiency is the thrust power generated by propeller divided by the shaft power, so total power that is provided to the propeller. And on that, what is the total thrust power that is generated, which is going to be T of thrust generated by the propeller times V infinity divided by the total shaft power, which is this. Okay, so this is the propeller efficiency, and the thermal efficiency is nothing but the shaft power by m dot f into q, or amount of fuel that is added, or amount of energy the fuel brings in. And the other performance parameters are propeller thrust, which is m infinity eta propeller into eta g into shaft power. So shaft power is the power available to the propeller, and divided by the V infinity. This is propeller thrust. Power available at the propeller is this. Shaft power is nothing but eta mt 1 plus f delta ht minus delta hc by eta mc. So this is nothing but, instead of replacing replace wt with delta h. That's all. Okay. So this is work available at the shaft. So similarly, we have the total thrust now is going to be thrust through from the propeller, plus some thrust is going out in the nozzle. So that is another thing. And yeah, so you can use this to find out what is the optimal power split alpha. And Based on the efficiencies, your optimal power split would look something like this. And I think you can do this derivation by your own. You will understand what are the efficiencies, and then overall efficiency is the propeller efficiency times thermal efficiency. And you can also have like a equivalent thrust power, which is nothing but the shaft power or the thrust power generated from the propeller plus the exit power, exit thrust. And yeah, and you also have total equivalent horsepower. Typically, power is expressed as kilowatt, but people would also like to know it in terms of horsepower. So you can also rewrite with the uh, factor included here. The 375 is added to convert the kilowatt to in horsepower. You also have the specific fuel consumption. Equivalent specific fuel consumption is nothing but m dot f by equivalence shaft power in horsepower. Similarly, you also have brake specific fuel consumption. So here, to find the thrust, you can use this Bernoulli equation to find the thrust. Uh, for that, you would need the inlet velocity and the exit velocity. Okay, all right. So you also have two spool turboprop engine where there are different configuration. So booster and HPC is in the same spool as HPT, and propeller is in the LPT. So and similarly, booster and propeller will be in the LPT, and HPC will be run by the HPT. So there are different configurations, and then there is also three spool turboprop configuration. All these configurations are there. And what you also have is we were studying this intercooler and regenerator for turbo fan engine. A similar, uh, turboprop engine you can construct with intercooler and regenerator. And here the comparison, this is a bit interesting. So you have for turbojet you have like low thrust and low v infinity. So if your aircraft is running at a lower velocity, or its aircraft speed is low, then you will have lower thrust. But for the low velocity you can have high thrust if you are running turbofan. And in turboprop you will have very high propulsive efficiency at low velocity. And turbojet is high, you know the specific fuel consumption. Turbofan is better. The turboprop, it's you expect it to be slightly lower, but it is sometimes complicated. You can have sometimes lower TSFC, sometimes higher TSFC. All depends on the power split and the efficiencies of the individual components. Um, but typically you will have lower specific fuel consumption. Okay, the frontal area is small for turbojet, but it is in for turbofan you have low noise, low uh, propulsive efficiency at a very high velocity, because if velocity increases you will have a lower propulsive efficiency. But it is also, but the efficiency is greater than turbojet, that we are sure. In turboprop, since the propeller is rotating, you will have a very high noise, but that's not the case for turbofan engine. You will have a low noise. Okay. All right. Similarly, you also have. I think this I no need to explain you. This is a similar curves that we have when we increase the compressor ratio, how the thrust is going to vary, specific thrust, um, specific fuel consumption, and efficiencies. If you have any doubts in this, please let me know. It's straightforward reasoning now that you all are experienced in this. All right, so let's get back to what the problems that we have. So I'm going to solve one question related to turboprop engine with intercooler and regenerator. So in the uh, in the lectures you must have seen professor solving a turboprop engine. I'm going to take the same turboprop engine, but introduce intercooler and regenerator, and we will see what is its effect. So From the last week, we know that when you add intercooler and regenerator, your efficiency increases, your fuel consumption reduces, but that's for turbofan engine. We expect a similar behavior for turboprop engine, so that is what we are going to solve today. The TS diagram would look something like this. So from infinity to 2, you have a propeller across which the pressure rises, and from 2 to 24205, 2 is low pressure compressor, and then you have intercooler which reduces the temperature slightly, but you also have pressure reduction because of the pressure losses. And because of this temperature reduction, you will have then you have a high pressure compressor which is going to increase your pressure and temperature um, to 3. And then from 3 you have regenerative heat, and then you have combustion chamber to that will reach the T4 TT4, which is the combustion chamber exit temperature or the turbine entry temperature. And from 4 to 4.5, you have high pressure turbine, which is running the compressor from 27 to 3. And from 4.5 to 5, you have power turbine. And from 5 to 7, you have regenerator, which is going to heat up the incoming air from the HPC. So from 3 to 3.3 to 3.5 or 3.5 or whatever, from 3 to 3.5, you have it is heated by the regenerative heat, not the fuel. From 3.5 to 4, you are it's been the energy is added in the combustion chamber, okay, which is coming from the fuel. From 7 to 9, you have nozzle, okay. So this is the TS diagram. So this is the question I'm going to solve today. A regional passenger aircraft cruises at an altitude where ambient pressure and temperature are 38 kilopascal and minus 30 degrees Celsius. The aircraft is powered by twin shaft free turbine turboprop engine and cruises at an altitude of 320 km per hour. The core mass flow rate is 2 kilograms per second. Design power split between LPT and the engine nozzle is 0.95. Okay, so the power split is what is the on the total delta H that you have at the end of the combustion uh, at the end of the HP turbine where you used it to run the HP compressor. The total power you can divide into some of them to run the LP turbine, remaining to how much it has to go to the nozzle. Okay, all right. So that design power split is 0.95, and the LPC pressure ratio, HPC pressure ratio, and turbine inlet temperature, intake pressure recovery, all these things are given. Additionally, these are same as the problem that we solved, solved by professor. The intercooler effectiveness and pressure loss is 0.85 and 3%, and the regenerative effectiveness and pressure loss is 0.8 and 3%. So these numbers are slightly lower. I mean, the effectiveness is slightly lower and pressure loss is slightly higher compared to the intercooler and regenerator that we used for the turbofan engine. You can also use the same numbers and see what are their effects. I'm going to go with a slightly lower number, maybe like poor intercooler and regenerator. How would that perform? Okay. So these are the given and the efficiencies. So without intercooler and regenerator, these are the numbers that we got. Net thrust is 4.37 kilonewton. Uh, the equivalent shaft horsepower is 603.24 horsepower. TSFC is 10.52 milligrams per Newton second. The ESFC equivalent specific fuel consumption is 0.605 pounds per ESHP hour. Propulsive efficiency is 83, thermal efficiency is 24, and overall efficiency is 20%. Okay. Now, the way we are going to calculate is similar. The inlet, and then you have a LP compressor, which is going to increase your pressure by 2, and you have a intercooler where the cold flow of the intercooler is going to be simply air, okay, which is entering at T infinity. Okay, so since this entire engine is exposed to the ambient, um, this intercooler is also exposed to an ambient, so air directly, which is ambient air, will enter, gets heated up and goes out. So that is one difference compared to turbofan engine, where the turbofan engine is the where you have the air from the fan in the ducted fan will enter the intercooler, gets heated up and goes out. Here it's slightly different. T0 infinity air enters and leaves. Okay. And then you have HP compressor across which the pressure rises 3.15 times, and then you have a regenerator. Regenerator, some heat is added, and then combustion chamber, some more heat is added. The TT4 is 1212 Kelvin, and the combustor, from there you have HP turbine which runs the uh, HP compressor, and also here the LP compressor, and then you have LP turbine which is going to run the propeller directly. Okay, and the LP turbine exit is fed into the regenerator to reheat the reheat the air from the HP compressor, and the remaining is going to go through the nozzle and exit with pressure, temperature, and velocity. The pressure, temperature, and velocity. Okay, you can use this pressure, temperature, and velocity uh, to find the thrust from the nozzle. You can use the LP turbine based on the power split. You can find the propeller uh, power and also thrust. Okay. So inlet from the ambient temperatures 32 kilopascal, 88.8 meters per second to 43 Kelvin. So flight Mach number uh, is 0.28. This is taken from the lectures. So here there is no change. We just introduce intercooler and regenerator. So we are expected to have same value of P02 and T02, which is 39.32 kilopascal, and temperature is 246.81 Kelvin. Okay. Now across the LP compressor, your pressure rises from 39.2 to 78.64 kilopascal, and here the difference is in the um, in uh, the problem that we solved in the lecture is we have like one compressor, so across which the pressure is climbing to 6.3. Here it is divided into LP compressor and HP compressor, because in between them we are adding the intercooler. So this 6.3 pressure rise is coming from two the pressure ratio of 2 is coming from the LP compressor, and the remaining 3.5 is coming from the HP compressor. So that's why at the exit of the LP compressor you have pressure to be 78.64 kilopascal, and therefore temperature to be 312.43 Kelvin. And after that you have an intercooler where the temperature that enters the temperature of the cold air that enters the intercooler is the ambient temperature, which is at 246.81 Kelvin. Here it's a stagnation temperature. Ambient temperature is lower, right? So what was the ambient temperature? Ambient temperature was 243 Kelvin, but the entire aircraft is moving at 0.28 flight Mach. So the stagnation temperature is 246.81 Kelvin. So that's the temperature that we are using it here, and effectiveness is 8.8. So the total temperature change is T025 minus T027 divided by T025 minus T0 infinity. Okay, so this is the actual temperature change divided by the maximum possible temperature change that you can get, which is the intercooler effectiveness formula. So you rearrange them to find the temperature at the exit of the intercooler, which is 256.65. So from 312 it has reduced to around 60 kelvins. Okay, and the intercooler exit pressure is around 76.28 kilopascal. A 3% loss of pressure has happened. From 78.64 it has reduced to 76.28 kilopascal. And in the HP compressor, the remaining pressure rise is happening, which is from 76.28. Your pressure rises to 240.28 kilopascal. Okay, so since you have intercooler and the 3% pressure loss in between LP compressor and HP compressor, the in the um problems that solved in the lecture, it was around pressure was around 247 kilopascal. Now your pressure is slightly low, which is 240.28 kilopascal. and the temperature is somewhere around 379.17 Kelvin. So as usual, if since there is an intercooler, you expect the temperature to be lower at the exit of the HP compressor. And also, um, the work done by the HP compressor is going to be slightly lower. Anyway, that comes while doing our calculations at HP turbine. The next component that you have is the regenerator. For the regenerator, what you need is the cold air is going to be from the exit of the HP compressor, which is at 240.28 kilopascal and 379.17 Kelvin. So for the compressor exhaust, this is going to go through the regenerator, and there's a pressure loss of 3%. So we can calculate that, which is around 233.07 kilopascal. And for to find the temperature at the exit of regenerator, you have to use effectiveness formula, which is around zero point 0.8 for this regenerator. So here the effectiveness is going to be 305 minus 3 T03, which is the actual heat transfer, divided by the maximum possible heat transfer is nothing but T05 minus T03. Okay, here T035 minus T03 divided by T05 minus T03. Okay. Now the only problem here is we do not know both T035 and also T05. So the problem is, what is T05? Without knowing the exit of the um, power turbine, or without knowing the temperature of the gases that exits the power turbine, we cannot really find the temperature at the uh, exit of this regenerator, okay, for the compressor exhaust. So there is one, so like we ended up having four unknowns in the previous turbofan with the engine with intercooler and regenerator. We will also have some number of unknowns here, and we may need to do an iterative procedure to solve this problem. Um, yeah, so for that we need to find out what are the equations that we need to solve. So from here, this equation has two unknowns, which is T035 and T05. Without knowing T05, we cannot do. So let's try to find out an equation for T05. T05 is going to come from the power turbine. So let's calculate for the power turbine. So ideal per unit mass power available at the station 4.5 is, which is the HPT exit, is going to be equal to H 04.5 minus H9I. H9I is the exit. Okay, so total energy is going to be from H4.5 to H9I. Okay, so that is nothing but equal to uh, power PI is the ideal power per unit mass of the gas, which is m dot c times 1 plus f. So 1 plus f is added at the combustion chamber. So this is the ideal per unit mass power, which is equal to H 04.5 minus H9I. Okay, 9I here it's because ideal expansion from, if you allow the gases to expand from 4.5 to 9 ideally in isentropic way. Okay, so this is a isentropic process. If you allow it to expand, what is the total amount of energy that can be extracted is what we are trying to get from here. So which is going to be H 04.5 minus H9I, which is equal to H 4.5 into 1 plus. You can write it in terms of temperature, and then you can convert it in terms of pressure. So it's going to be 1 minus, so since this is also CPH, this is also CPH, you can take it common CPH times T04.5, which is basically H04.5 equal to 1 minus T9 by T04.5, where T9 by T04.5 can be, based on isentropic relations, can be replaced as P9 by P40.4.5 power gamma H minus 1 by gamma H. Okay. Now power delivered, this is the total power available at the exit of the HPT turbine, but power delivered to the LP turbine can be calculated by the power split factor. So which is going to be the total power, this is the total power multiplied by the alpha times the efficiency of the LPT. Okay, so which is m dot c into 1 plus f into H 04.5 minus H05. Okay, and this is nothing but this entire power multiplied by alpha power split factor times the efficiency of the LP turbine. Okay, so that efficient LP turbine also has an efficiency. So if you multiply them, then that is the total amount of power that is extracted at the power turbine, which is m dot c into 1 plus f h 4.5 minus h 0.5. Okay, so please be very careful in understanding how this equation is written. It's slightly trickier. So this is the total power that is delivered. That is delivered from the LP turbine. Okay. Now you can rearrange this relation to find out uh, T05, because we are interested in T05. This is CPH. You can take them out and you can cancel them. If you rearrange it, you will end up having T05 is equal to T04.5 minus alpha eta LPT T04.5 1 minus P9 by P04.5 gamma H minus 1 by gamma H. Now the problem is we found the equation for T04.5, but this equation has we found an equation for T05, but this equation has two more unknowns. So the question is, what is T04.5 and what is P04.5? Okay. So for that, you need to know the amount of work extracted at the HP turbine. So that's what we are going to do, HPT work. The HPT work is used to drive both HP compressor and the LPC compressor. The LPT turbine is used to directly drive the propeller. Okay, so that's why LP turbine is also called power turbine in this case. Anyway, so the mechanical efficiency of HP turbine times the work done by the HP turbine is equal to the work delivered to the HP compressor and the work delivered to the LP compressor. So this is similar HPT work, the energy balance that we already know. So you can substitute the temperatures to find out what is T0 4.5. So if you substitute this, you will end up having this as your final equation, which will have f also as an unknown here. So to find f, we go and we use the combustion chamber equations to find the f. The other thing we also need is P04.5. Till in our previous turbofan engine, we never really cared about pressure while doing this thing, but in here, the previous if you go back, the previous equation requires P04.5. So that's why we need P04.5 also. So let's so for that we have the turbine pressure ratio, isentropic relationship for efficiency, that will give you P04.5. So this is the same turbine equations that we already know, but this requires us to find P04, and for that we need both P04 and F. For that we have to solve the combustion chamber. In the combustion chamber, the pressure losses we already know. So from the regenerator, the exit of regenerator, we know the pressure. So from there we can find the P035, which is 233.07 kilopascal, which we already know. And across the combustor, you have 2% pressure loss. So based on that, you have 228.41 kilopascal. So P04 is already known. So we don't need to have an equation for P04. Other thing is we also need to find F, but F you do like you perform an energy balance in the combustor. The energy of the air that is entering plus the energy of the fuel times the efficiency is equal to the total mass times CPH times T04. Okay, you rearrange them to find F, but that will lead you to another unknown called T04, T035, and that is nothing but the regenerator exit, right? So the regenerator exit is what we initially wanted. So you have like a 5 unknowns. So what you do is you perform an iterative task. You initially guess a f, and then you using that f you find T04.5, and then you find P04.5, and then you find T05, and then T035, and then finally f. And if the f is same as the initial guess, then you no need to go again. If F is different, then you continue uh, substituting it again back to first equation T04.5. You repeat this process. Typically, it would take one or two, three iterations. If your initial guess is very good, it will take two iterations. If not, maximum three, four iterations. That's all. So that will give you the values as F to be 0.01634, and the other temperature and pressure values you will get. Okay. So here I used some a small MATLAB script to do this, but you can also do it by hand. You will end up having same relation. All right. So now that we know T035, we can solve the combustor. So we know regenerator exit, which is P035 and P035. Based on that, you can solve the combustor to find F, and P04 we already found. So F is also F actually, the what do you call, the iteration procedure already would have given F, but here I'm just repeating the same calculation again. So where F is around 0.0163. So you can look at it for the problem that we solved in the lecture. It's around 0.023. Now it has reduced a lot, 0.01634. Okay, so fuel consumption has reduced, but let's see whether the TSFC also has reduced. All right, so then since we know pressure and temperature at the exit of the combustor, we can mm, solve HP turbine equations to find the pressure and temperature at the exit of the HP turbine. So for that we do energy balance, and you end up having T05, which is 1049.03 Kelvin. You expect the temperature at the exit of the HP turbine to be higher than what we solved before. The reason is, since the HP compressor is going to the work done in the HP compressor is slightly lower, um, because of the intercooler, you expect temperature to be slightly lower. So sorry, temperature to be the work done to be lower, so the temperature to be slightly higher from the HP turbine exit. Okay, so that's why you see around like a 20 Kelvin difference from what we solved in the lecture and what we are getting here. Okay. All right, so we'll also find P04.5, which is from the turbine efficiency. That will give you 114.12 kilopascal. Again, we did not expand it much because that is enough to drive both the compressors. So once we know the pressure and temperature at the exit of the HP turbine, now you can proceed with the calculations of the power turbine or LP turbine, and that is going to drive the propeller. Okay, so the total power available at the LP turbine is nothing but the m dot c into 1 plus f h04.5 minus h05, which is nothing but the alpha times the efficiency times the total power available at the exit of the HP turbine, which is this big equation. Okay, so we can find the temperature. We already used it to in the iterations. That is around 834.86 Kelvin, which is slightly higher than the what we solved before. And the power available for the LP turbine is also 501.51 kilopascal. So this power is also slightly higher. Okay. Um, all right. So we were getting the power at the LP turbine was around 478, and now you have around like 20 kilowatt power higher from the LP turbine. Okay, this is not the power for the propeller. I mean, this is the total power going to the propeller. We will find out what is the propeller power. Okay. Um, Now we can also find the pressure, which is coming from the efficiency, which is around 40.46 kilopascal. So the total properties at the power turbine exit, you can find out to be 834.86 Kelvin and 40.46 kilopascal. Okay. Now the remaining gas is going to go through the regenerators. And across the regenerator, you have a pressure loss of 3%. So which reduces your pressure from 40.46 to 39.28 kilopascal. And you can also do energy balance to find out what is the temperature at the exit of the regenerator, so that the remaining gases expands in the nozzle. So that temperature is around 522.25 Kelvin. Okay. So from 834, the around roughly 300 Kelvin has been lost in the regenerator, which is used to heat the um, air from the HPC exit. All right. So the temperature and pressure at the inlet to the nozzle is 39.25 kilopascal and 522.25 Kelvin. So from the choking condition, you can actually find out what is the critical pressure, which is around 20.92 kilopascal. This is less than the ambient pressure, which is 38 kilopascal. So it is typically expected that turboprop engine is typically the nozzles are unchocked. Okay, and therefore the exit pressure is equal to 38 kilopascal. And you can also find the temperature and velocity. So the main here is velocity. You can find it out to be 97.12 meters per second. Since you have extracted a lot of power, you have a lower velocity at the exit. So in the nozzle, we calculated it to be around 165 in the lectures. But here, because of intercooler and regenerator, temperature has reduced, and therefore your velocity at the exit also has reduced to 97.12 meters per second. All right. So then the temperature T9I, which is isentropic expansion in the nozzle, is around 518.07 Kelvin, but the actual temperature is going to be around 518.16 Kelvin. Okay, slightly higher because the process will not be isentropic and you have nozzle efficiency. Okay. So therefore, you can find the Mach number at the exit of the nozzle, which is around 0.218, which is also expected, and it is subsonic. Okay. All right. So now we can find the propeller thrust. So what is the amount of thrust generated by the propeller? So that is going to be around the propulsive efficiency, the propeller efficiency times the gearbox and the uh, efficiency used to transfer the LP turbine power in the spool, and also the power extracted at the LP turbine divided by the V infinity. So that we can calculate it to be around thrust to be around 4.352 kilonewton. So which is slightly higher than what we calculated before, 4.21 kilonewton. And similarly, the core thrust is going to be simply the m dot into V plus the pressure thrust, where m dot here is m dot C into 1 plus F into V9 minus V infinity. And the pressure thrust is not being added here because nozzle is unchoked, so pressure P9 and P infinity are same, so that's why it's a 0. So this T core is going to be very low, which is 19.65 newtons. So if you remember uh, the thrust generated by the core flow typically are very high. It will be typically in the kilonewton range for turbofan and turbojet, but in turboprop engine, for this case, it's around only newtons range. And if you compare that with the propeller thrust, it's around uh, it's like an order of magnitude difference. So the total thrust is just addition of propeller thrust and core thrust, and thing that is not going to change from 4.35 as we rise to 4.372 kilonewton. So the total thrust is not much of a difference. So basically, the core thrust kind of went into the propeller thrust from the lecture problem to this problem. Okay. So overall, the total thrust has slight increase, 372, but in lectures we got only 4.37 kilonewton. Okay. So there's a slight increase, but what we know is the F has reduced a lot from 0.028. If you remember, it has reduced to 0.016. So you expect this problem to have a lower specific fuel consumption, and that is what we will be getting. So before calculating the specific fuel consumption, let's calculate the propeller power, the power at the propeller, which is going to be total power extracted at the LP turbine my times the eta m of the LP turbine, mechanical efficiency of the LP turbine, times the gearbox efficiency. So there is some efficiency, there's some loss of power due to the transmission of the power from the LP turbine to the gearbox, and gearbox itself has an efficiency, which is gearbox efficiency. So remaining is the total propeller power, which is 471.67 kilowatt, and the propeller itself has an efficiency. Okay. Um, yeah. So this is the total power at the propeller, which is 471.67 kilowatt, which is higher than the 450 kilowatt here. So the power produced by the core engine is around 1.746 kilowatt, which is nothing but the thrust of the core times the V infinity. Power produced just by the core engine is very less. The equivalent shaft horsepower is nothing but the shaft horsepower plus the P of core divided by 0.476 times the propeller efficiency. Um, so then you can substitute these numbers. It would be around 635.12 horsepower. So which is higher than the uh, higher for a intercooler and regenerator cycle. Okay. Now comes the fuel consumption. Thrust specific fuel consumption is going to be now the thrust is divided by both propeller and core. So you have two thrust that you need to add it in the denominator. So propeller core and propeller thrust, or you can just substitute the overall thrust. And that is going to be around 7.47 milligrams per Newton second. So which is much lower than from 10.5. It has reduced a lot, right? 7.47. And finally, what you have is equivalent specific fuel consumption, which is it's not in SI units. I think it's in imperial units, I guess. So equivalent specific fuel consumption is nothing but m dot f divided by equivalent shaft horsepower. So that is around 0.408 pounds per shaft horsepower, equivalent shaft horsepower per hour. Okay. So that is also reduced from 0.605 to 0.408. Okay. Now let's find the efficiencies. Thermal efficiency is going to be equivalent shaft power. This is not horsepower. It's again we are back to SI units. Equivalent shaft power divided by m dot f into QR. That is around 34.36%. It is higher than uh, the turboprop engine without intercooler and regenerator. And the propulsive efficiency is around 82.38%, slightly lower. And the overall efficiency is roughly 28.31%, is high. Okay, because the thermal efficiency has increased. So finally, here's the comparison. Without intercooler and regenerator, we get the thrust to be around 4.37 kilonewton. With intercooler and regenerator, we get the same thrust, not much of a difference from 4.37 and 4.372. But where the difference is, like in the horsepower, there's a difference, and the specific fuel consumption has reduced, both equivalent specific fuel consumption and thrust specific fuel consumption. The propulsive efficiency is almost same. The thermal efficiency has improved a lot, and therefore your overall efficiency has improved a lot. Okay, so this is the benefit of having an intercooler and regenerator. But what is also true is um, you are increasing the number of components, and yeah, it requires a high maintenance. Reliability issues comes into picture, and all those things are there. Maintenance is required. Safety measures needs to be taken care. So those things you need to take care before devising such an engine. Okay. All right. So next week, as I said, we will study about turbo shaft engine. And if you have any questions regarding the turboprop engine, please let me know um, in the in the common forum. I would be happy to answer. If not, you can come next week, and I will be happy to answer there. All right. So this is what I have today, and yeah, thank you. See you in the next week for turbo shaft engine.